Hi everyone, this is Mani Krishna Kumar. Today I am going to review about microfabricated diamond by using tensile elasticity method. Uh, how they are really using the tensile specimen for diamond, and how the load acting stress strain curve, and micro vaporization method, how it's the diamond they produce. For the slides we can go in depth. Then they are using scanning electron microscopy and TEM and ELS, and further images how the diamond really uh, working. The microfabrication technologies, the primary objective is miniature, bulk produce at low cost, and moving components, etc. The secondary features are described here. And this flow chart, how we are producing diamond. There is a different kind is there. It's mainly we are going to talk about chemical vapor deposition, how they are producing. This is the flow chart, how the chemical vapor deposition method is working. As we know all, the diamond is the Mount Everest of electronic and photonic material, and it's used widely. And how it's working, ultra wideband gap, and it's used for MEMS, quantum, photonic devices, array and strain, engineering transistor, and other applications. And further applications we going to describe in the next. From this slide, we can see the diamond how really useful for different industries, different applications. There are so many applications. It's widely used. It's described here, and these images A, B, C, D. It's taken from TEM, and the microstructure images for the diamond bridge samples. It's described here, and the load and the displacement, how it's acting. We can take from this chart. It's perpendicularly equally going up for the unloading and the loading. From this chart, these images we can taken from loading and unloading tensile experiments along the 101 directions. These images A, B, C, D, E, F. From here we can compare the strain values for here. Then it's plotted in the chart and compared by different specimens. And statical tensile results for the 100 and the 101 and 111 oriented diamonds in the directions. We can see the tensile strength and tensile strain law. And these are the microstructure images from the diamond bridge samples. And the scanning electron microscopic characterization of diamond, it's from different viewing, side view, top view, and etc. You can see this. And these are the amorphous layer, how it looks, the sample surface, and these images for the 100 direction, the bit sample. Here we can see the 6.8% of failure strain. And in situ of scanning electron microscopy, tensile setup for the staining diamond array samples are here. Images A, B, C, D, E. And from this chart, from stress strain converter described. And these are the samples for the different crystal directions 100, 101, 111. In situ of tensile strain of the single crystal diamond, which showing a maximum strain of 9.7% from this. So we can say that is 9.7% the maximum strain the diamond can get from this picture. The stress strain down or described. different features. The William Jones diamond private cells without strain. These are the Z and X Y axis, how it's working, and the lattice vectors B1, B2, B3 are marked. These are the lattice vectors, and this picture shows uh, calculated energy band gap in high to low, and for the directions 100, 101, and 201, and the picture B describe about the oriented diamonds for the different directions. You can see from high to low how it's showing, and this is the symmetry variation of diamond in billion terms. You can see from A to E how it shows the values. The maximum strain in the different orientations at 12%, and this is the calculated diamond band structure. The band structure for 100, 101, 111, and from the chart we can see all three directions how its band gap and the uniform strain is working, and this is the values for K part, and from the symbols K1, K2, K3. This is the characterization of electronic band gap. You can see from A, it's a crack found on the center. This image is taken from ELS, and this B is from STEM. It's a crack found on the center of it's enlarged view from STM, and it's ELS. This chart is showing that the energy value of 5.3 and then 4.3 electron volt, and it's showing about 3.6 electron volt for the energy loss. And the overall advantages are, as I told before, so how it's the band gap really working for the MEMS, photon devices, and the quantum information process, etc. And then by avoiding the methods like ELS, STM, how it's really working, and on the basis of our calculations, in an indirect and direct band gap transition may be possible with tensors larger than 9.9% along the one directions. Thank you everyone. Thanks for watching.